In this screencast, I'll show you how to model a particular system and then using appropriate boundary conditions, derive an equation to predict the concentration. And so what we have are these chemical agents that are added to blood vessels via a uniform coating on the inside of the tube. So in this one, we'll derive the equation for the concentration exiting the blood vessel. And in the second screencast, we'll use that equation and properties given to us to solve for the final concentration. So the first thing is that we have a process that is dominated by convective mass transfer. So what that means, instead of using the continuity equation or Fick's law that we've used for diffusion limited or dominated processes, what we do instead is start with a general mass balance. So let's draw a picture here. So we have this vessel and we have the blood going in and coming out. In addition, there is this coating here that releases the chemical agents into the blood. So the first thing we have to ask ourselves is it steady state? And the best way to look at it is if you look at a point here, point 1, and you sit there for 10 minutes, is the concentration going to change? And the answer is no. So it is a steady state problem. However, if you look at a point further down the tube, the concentration will have changed. In other words, we're just going to look at that mass in equals our mass out. So what we're going to do is look at the solute in a differential element. So going into that element, we have solute from the entrance as well as from the sides. So going in, we have the concentration of A times the velocity times PD times pi d squared over 4 at Z. So that's going into that element. In addition, we have convective mass transfer coming in from the side. So added to that is this convective mass transfer coefficient, K sub L, and this driving force, which is the difference between the concentration at the surface and the concentration at a particular point. And so this flux is multiplied by the surface area, pi d delta Z. So that's what goes in. Let's take a look at what goes out, and that's again this concentration of A times the velocity, pi d squared over 4, and now we're looking at it at Z plus delta Z. Let's first multiply the terms by 1 over delta Z. And now we're going to put the in and out terms together. So if we divide everything by this delta Z, and we get rid of this pi d pi, and this will be left with d pi, this will just be left with d, we're left with K sub L times the difference in these concentrations equals V d divided by 4, our Ca at Z plus delta Z minus our Ca at Z, and the entire thing is divided by delta Z. So if we take the limit as Z approaches 0, we're left with K sub L times this delta C equals Vd divided by 4 dCA dZ. So let's look at our boundary conditions. We know at Z equals 0 that the concentration is 0, as Z is the beginning of the tube, and at Z equals L, our concentration is some kind of final concentration, which is what we're looking for. So we do the integration, leaving our constants out here. 0 to L dz equals the integral from 0 to the final concentration dCA CAS minus CA. Then, after we've integrated this, we find that 4 times K sub L times the length divided by the velocity times the diameter equals the natural log of the surface concentration divided by the surface concentration minus the final concentration. So if you simplify this and solve for the final concentration, you're left with the surface concentration times 1 minus the exponential of minus 4 times this mass transfer coefficient times the length of the tube divided by the velocity times the diameter. And although in this particular problem we solve for the final concentration, you can actually find a concentration anywhere along the length of the tube by, instead of using L, you use X, where X is the length of the tube that you're looking at.